This video presents the concepts of associated with linked list or linked nodes, which are a important concept in computer science and have a wide applicability in different data structures. Recollect that there are a large number of data structures that we typically work with, and each data structure provides different trade-offs in performance on different operations. For instance, some data structures finding might be fast, but the order of the data may not be preserved. Or in some cases, inserts is fast, but finding information may be slow. So different data structures provide different types of trade-offs, and these trade-offs are magnified as the size of the data stored in the data structure increases. Consequently, data structures have to be selected to best meet the needs of the software application. And this is very critical operation for designing and developing good software. And the choice of the data structure can make or break the software systems, particularly as the size of data grows. Consequently, it's important to understand these data structures at a fundamental level. Recollect that a data structure is a part or unit of a program that handles CRUD or create, retrieve, update, and delete operations. This includes inserting data, removing data, so on. And this part or unit of the program that performs these operations on the data is called a data structure. Keep in mind, in object-oriented programming languages, typically these data structures will be implemented as classes or a hierarchy of classes as shown in this diagram, and they might use inheritance and polymorphism to implement the different operations of the data structure. It is also important to keep in mind that the idea of an abstract data type is one that provides the key or specific properties of the data structure. Keep in mind, abstract data types tell what operations are supposed to be supported. So for example, the list says what are all the operations a list should support, versus the data structure provides the concrete implementation on how those operations are done. We have seen array list before. Today we're going to get into linked list. Recollect that array list uses a generic array for underlying storage and eases operations on the array. So for example, when the array needs to grow whenever it is full, so let's say we want to add 5 to the end of the list, the array list internally creates a new array and copies all of these elements over. And recollect that copying n elements to a new array is big O of n, and this can be time consuming when we have to copy millions of numbers. Similarly, the array list eases insertion, find, remove operations. So for example, let's say we want to insert 8, then the array list internally moves the elements to create space for 8. And this operation of copying or moving elements is again big O of n, and this can be time consuming when the array is large. Correspondingly, remove operations are also big O of n. And when you think about this, notice the behavior of the array list or arrays. Operations are typically performed on a per element basis. That means we are moving one element at a time. And then operations on one value can impact many other values. So for example, if we insert or remove the first element in an array list, you're impacting the entire list of elements, which is time consuming. So the question comes, is there a better way to address some of these issues, as in better way to store data so that we don't have to impact all of the elements just when one value needs to be added, removed? And this is where we come into this idea of linked nodes or linked lists, which are a chain of individual values. In this context, a node or a linked node consists of a pair of information. One, a value that it is storing, and second, a link to the next node in the chain, if there is any. So here's a Java class that implements this, just a simple Java class. It is parameterized on some generic type T, so we can store different data types, different objects of different types into these nodes. So it stores the value associated with the node, and there is a next, which is like a link or a pointer to the next node in this list. So for example, we can create 3 separate nodes. Let us assume these are strings, and here's the Java code to do that. So you create a node, just going to hold a string with A, B, and C. Notice that these are 3 independent objects, N1, N2, and N3, right? These are independent objects. Now we create a list or a linked list or a chain of these nodes by connecting or wiring these nodes in the correct order. So a list is created by linking these nodes together. So let's add a couple of set methods to set both the value and set the next node in that list. So here we can link these nodes by linking to saying for node n1, the next node is going to be n2. So the next here will point to n2. Similarly, for node n2, we're seeing the next node is going to be n3, and this link is set up to point to next. And then to indicate the start of this chain, we will typically use a variable called the head, which indicates the start of the chain. The name of head, it's just a variable name, but that's the convention. Typically, we'll have a head that'll be the start of the chain. And now when you're given the head node, each node basically says, what is the next node in the chain? So by traversing these links, we can go node by node and get the values and essentially form a list of values. And this type of a list is called a linked list because it's got links in each node to the next element. Keep in mind, once we have set up the links, the list can be traversed node by node, starting with the head node. So here's a simple algorithm logic to trace or traverse the list. This one simply prints the value on each one of the nodes. So here, given the head node, while the head node is not pointing to null, so the last node here will be set to null. That'll be the last node. The link in the last node will be set to null, so we know that's the end of the chain. So while we are not at null, we print out the current node's value. So starting with the head, first it will print A. Then we say current equals current.next. So current will move and point to this node now because A's next node is N2, so it'll point to node N2, now current. And then you'll print current's value, which will print B, which is the current value. Then we move current to the next node, so current then moves here to the third node. It'll print C, and then current will traverse and its value will be set to null, and this while loop terminates. And it prints A, B, C. This is a simple approach to traverse the list of nodes. Keep in mind, inserting a node after an existing one into the chain is pretty straightforward. It updates just requiring two links in that node. However, there's one special case here. If the list is empty, that means the head will be null. Then the head is set to point to the new node, so that it points to the beginning of the list. So here's a simple way to update the two nodes, and here's an example how to use it. So here we're going to create a new node with the data D. So let's say we create a new node, and I want to insert D after N2. Yeah. So I'm going to say N2 after N2 to the N2 node, insert N4. So here what it does is it goes in. This is N4 is the new node. It says new node.next is equal to N2's next. What is N2 currently pointing to? It's pointing to N3. So D4's next will be first set to point to N3. Yeah. Now notice how it is D's initial. In the next step, we set N2's next, this next, to point to the new node. So instead of it pointing to C, we change it to point to D. Now you notice how the chain is. First it will go to A, when we traverse it to B, then it will go to D, and then come to C. Yeah. So inserting a node basically required us to update this link. So set this link first to the next, and then update the existing link to point to the new node. Those are the two operations that were needed. Now let's look at the converse operation of removing. Again, to remove a node, it just requires updating one link in this list. Yeah. So let's look at if you want to remove this new node that we added, N4 was added. We want to remove N4 from, so we are modifying N2 to no longer point to N4. So we're saying N2, remove N4, which is the next link. So it goes in here, it says N2's next is going to be modified to the delete. This is the node we are removing. N4 is the one we are removing. So it's next. What is D's next? It's pointed N3. So N2's next, instead of pointing to D, will be modified to point to N3. Now, when you traverse the list, you'll go from A to B and then B to C. You will never see D. And this node D will eventually be garbage collected and removed by the Java's garbage collection system. So removing a node after a given node is pretty straightforward and requires only updating one link. Now contrast this with array lists. If you were to remove a node, you'll have to shift all of the other values in the list. Versus here, it just requires one. It's a constant time operation. Notice that this is just one statement, a constant time operation. Now let us look at the operation to get a node at a given index position. Recollect that when you say ArrayList.get of I, this is a big O of one method, right? Because directly you can get access from that array. However, the gotcha with linked lists is, in order to get that node, you have to traverse the list node by node, because we have the only link that we have is the head. So in order to get to C, you will have to start from head, go to A, then go to B, and only then you know where you can get to the node that contains the value C, or the ith node in this case. Okay? So for example, here's the logic. You're saying you start with the head node, current is set to head, and then while I is greater than 0, that means we want more nodes, and the current one is not null. That means here we have a list of 3 nodes. If you want the 5th node, there is no 5th node, and this method is simply going to return null to indicate there's no 5th node. So curr.next, so we keep going to the next until the index becomes 0. So here, let's say starting from the head node, we want to get to the first node. This get method will be called, current will be set to head, I will be 1, which is greater than 0. You'll go to curr.next, you'll go to B, you'll say I minus minus, then I becomes 0, and then current will point to B, and it'll return node N2, which corresponds to B. That's what this method returns. It's also important to keep some of the other operations on linked list to keep in mind. These are all the special or edge cases that you'll have to keep in mind. If head is null, then the list is empty. Getting the first data item, you simply say head.data or head.value, and you'll get the first item. Seeing if the list has at least 2 nodes, first you know head should not be null, and head.next should not be null. So if head is not null and head.next, this link is not null, then you know you have at least 2 nodes. There could be more, but we know at least we have 2 nodes here. Getting rid of all nodes is simple. You simply set head to equals null, and the entire chain disappears. So the garbage collector will garbage collect the entire chain. Getting everything after the first node, again simple. You simply say head.next. Instead of pointing here, you simply set this to null. Yeah, you simply set this to null, and then boom, all of this magically goes away and will get garbage collected because the chain ends or is broken there. To get rid of only the first node, notice that this is very cool. You can simply say head equals head.next. So instead of head pointing here, it'll simply point at B. This will be the starting node now on the linked list, and this node will be automatically garbage collected by the garbage collector. So these are special cases and operations, convenient one-liner operations, and this is something for you to keep in mind or memorize so you can use these whenever needed. So here are key patterns to remember for linked list. To access any node, you will need to always start at the head node. So that's the first thing. Yeah, that's how the list works. You always start at the head node, and that's the only way to get to all of the nodes in this linked list. So the head node is the key. Inserting or removing a node, you need access to the node before the location. So that means if I want to insert a node here, I have to have some way to get an access to the previous node, or node B in this case. I have to have access to that. This is either to insert or to remove. You need access to the node before that location, so we can update the links in B. So here, if I add a new node, I have to update B's link to point to this node, and then this node to point to C, right? So you need access to B. Inserting at the head or deleting the head are special cases. So anytime you work with head, these are all special cases. You have to check and handle those appropriately. Setting a node's next reference to null will delete everything, or basically ends the chain. So if I set this entry to null, right? If this entry is set to null, then the chain ends here. So everything after that will automatically disappear. And these are all important key aspects that you'll have to memorize and remember when working with linked lists. Let's also look at the time complexity for operations here. Adding to the end of the list, array list is an amortized average. Array lists still have to grow, but the growth is not very often. So it'll be an amortized constant. So is it with linked list. All you have to do, adding a node at that end, if you have access to the previous node. This is assuming you have access to the previous node. It'll be a constant. Inserting, typically you have to shift n elements. Inserting at the ith position, you'll have to traverse the list to I minus 1 because you need access to the previous node. So both of these are big O of n constants. Inserting after a given node, you'll have to shift elements, but if you already have access to that node, it'll be big O of 1. Removing after a node, this is again big O of 1 to shift elements, but since you have access to that node on a constant time, you can do big O of 1. If you want to remove the ith element, in both cases you have to shift elements, here you have to traverse the list, so it becomes big O of 1. Getting the ith element. Notice that here it's big O of 1 to get the ith element, so access is very fast. But with the linked list, you'll have to traverse the linked list in order to get that information. Index of or find method both are big O of n because you have to linearly search the array or linearly search the linked list. Keep in mind, linked lists are best when most operations are inserts or removes. Runtime constants for a linked list is much higher due to memory allocation overheads. And there's also extra memory for link or pointer to the next node, something to keep in mind. And of course, in a general, adding to the end of the list, in a general case, this will also be big O of n, which will be the generic case. So that's something to keep in mind, is in a general case, it'll be big O of n here. As a wrap-up, linked lists are an important concept, so understanding helps them think differently about memory and problem solving. That's the real key out of this linked list, is that different way to think about things is kind of important. And they are a good substitute for array lists, but it's important to keep in mind the trade-offs between the two in order to design effective software. So you have to understand the time complexities of the different operations so you can choose the appropriate data structure. And linked lists have applications in many other areas of computing. So a lot of times file systems or how data is stored on disk uses kind of sort of a linked list. Memory management, how information is managed in memory, uses linked list. Operating systems, when multiple processes or programs are running, how those programs are managed and scheduled. There are applications in networking, data communication networks as well with linked lists. So it's important to keep this in mind, that linked lists, understanding linked lists will give you the ability to apply them in different ways in other areas of computing as well.